Okay, I guess you're here for more applications of vectors from section 9.4b. An airplane headed 28 degrees north of east is traveling at its cruising speed of 600 kilometers per hour. It is also benefiting from a tailwind of 90 kilometers per hour at 10 degrees south of east. What is its, meaning the plane, what is its ground velocity? Now, for starters, I'm going to go back into the original problem, and I'm going to tell you that 600 kilometers per hour, that last zero, is significant. I'm going to use your notation that the book uses. And that final zero on the 90 kilometers per hour is also significant. But there's the airplane. Where is the tailwind? All right, my first thought on this is that I would draw the tailwind here, hitting its tail, going kind of in the same direction. However, these are vectors, and as long as we preserve direction and magnitude, we can move them wherever we want. So I'm going to move this 10 degrees south of east and 90 kilometers per hour down here. So sticking in right there is my 10 degrees south of east. And that line, that vector, has a magnitude of 90 kilometers per hour. And if you don't like the way that looks, you can move your airplane down here at the beginning of the vector, so the wind's kind of hitting it in the tail. But I'm actually going to let that plane fly right out of there and get it out of the way. What is the ground velocity? What is the resultant vector of those two? When I'm using a Cartesian axis, I like to use the parallelogram method. Now, if you prefer the tail-to-tip method, here I'm moving this one. Look, I'm putting the tail of this vector at the tip of the first vector that I drew for the plane, and either way you draw it, the resultant vector will go from the origin in this direction. All right, I think I need to shrink this a little bit, move it a little bit out of the way, because we're not going to solve this graphically, no protractors needed. We're going to do it by vector addition, by addition of the components of the vectors that are involved. Okay, so we'll let A be for airplane, and we'll let W be for the wind, and we will have a resultant vector. So yes, I've gone back to colors. It keeps me interested too. All right, our magnitude of A is 600. So the x component of A will be 600 times the cosine of the standard angle of 28 degrees. Standard angle because it's in the first quadrant. And the y component will be 600 times the sine of 28 degrees. Okay, but we do not have a standard angle for our wind. So let's convert the wind to a standard angle first before we get into its x and y components. Okay, so I've zoomed in on that wind vector. Okay, so the scale is different. That's why I've drawn it longer here. But what we're interested in right now is not the magnitude. We are interested in that angle. So what is the standard angle? If we go from the x-axis all the way around, it's 360 degrees minus 10. And let's go ahead and say also, which I should have said at the beginning, that 10 degrees, the zero, is significant. So we should have all of these being significant. Okay? So that degree measure is actually 350 degrees. It's not quite to 360, it's 10 degrees less. So 350 degrees. And then the x component of the wind will be, the magnitude of the wind was 90 kilometers per hour, and we're multiplying that by the cosine of the standard angle, which is 350 degrees. And then for the y component, it'll be 90 times the sine of 350 degrees. And now we can find our resultant. X component of our resultant and the y component of our resultant. If we add those up, those are the values we get. If you are asked to comment or report the x component and the y component of the vector r, then you do have to round those to how many significant digits? 2 significant digits, because that's the least number of significant digits we have up there, and you're doing multiplications. So that's what you go with. So if you had to report these, I'm not asking you to for this problem, but you would report this as 620 kilometers per hour in the x direction, and this would be 270 kilometers per hour in the x direction. But once again, that's not what we're getting at. Right now, we don't really care about this intermediate step, so we're not going to round it. We're going to use these values, and in fact, I suggest you use your calculator, and you go up to your calculator, scroll up, pick up the value you need, the actual formula, and bring it down here. Pick up the x component and square it. Pick up the y component and square it. Add those together, take the square root. You can do that all in one step on your calculator. And you should get a value of 673.205, blah, blah, blah. And that is what I'm going to be interested in. I want the magnitude of that vector, so I'm going to round it now to two significant digits. So 670 kilometers per hour. Once again, I was doing multiplication. And now we need to find a reference angle. That will be the inverse tangent of the absolute value of the y component of your resultant over the x component of your resultant, the opposite over the adjacent. And that value is 23.278812, which, to the proper number of significant digits, which is 2, is 23 degrees. So the ground velocity, so I'll make it green since it's ground velocity, the ground velocity of that plane, how it appears to be traveling from an observer on the ground. It appears to be traveling at a magnitude of 670 kilometers per hour and a standard angle, because we are in quadrant 1, the standard angle equals the reference angle. So the angle is 23 degrees. That's how that plane's flying. We're done. And we're done with the video. So I'll see you in class. We'll be practicing. See you then.